How's it going, guys? This video is going to be all about reaction mechanisms. We're going to talk about identifying intermediates, catalysts, and then we're also going to go over how to identify the overall rate law. So the first thing that I want to go over is the elementary steps. Elementary steps are a series of steps that comprise a whole reaction, and you can simplify them into these. So A yields B plus C, B plus C yields C and D, ABC yields DE, and so on and so forth. Essentially, what is relevant is how many moles of a reactant there are. So the products really don't matter for deciding the elementary step, or whether it's unimolecular, bimolecular, or termolecular. These ones down here I separated out because I think they're more likely to throw someone off. So bimolecular can also be 2A yields products. Even though there's only one reactant there's 2 moles of it, so it's going to end up usually being second order in the end when you have the rate law. So, and same thing with termolecular, it's based on the number of moles. So theoretically 3A yields products would also be termolecular. So that's just something to kind of watch out for and keep in mind. So I'll put this just to the side for now, and then we'll go over one more thing. So in terms of identifying intermediates versus catalysts, this is the simplest form that I can put it into, I think. Intermediates are produced and then consumed, so they go from the right side to the left side of a reaction. And then catalysts are consumed and then produced, so left side to the right side. There's other ways of kind of remembering them. Like I think I originally heard intermediates were just the ones that you cancel out, and catalysts are always in the first reaction as a product, and then as a reactant, and then in the last reaction as a product. But that's not always the case. In some cases, you'll find that isn't the case. So I think we'll just jump into the first problem, and then we'll jump back to that after. So here we have the decomposition of hydrogen peroxide occurs according to the following mechanism. We have these two reactions here, and then we have one is slow and one is fast. So what we're going to do here, we're going to start with the elementary steps. And I'm just going to kind of break this down into the questions that are typically asked. So the first one might ask, what are the elementary steps? In this case, what we have is here H2O2 and I-. We have 1 mole of each. So the first one, we'll say 1 and 2. This is going to be 1, that's going to be 2. 1 is bimolecular. So that would be the rate equals K A B, or K H2O2I. You can just sub in hydrogen peroxide and then I. And then the other one is going to also be bimolecular. And that's the rate is going to equal the exact same thing. We'll just say IO minus and H2O2. So there's our elementary steps. Now the next thing that we can do, we're going to look for the overall reaction, and we'll say, are there any intermediates? Are there any catalysts? So the way I most commonly will find this one written out is, let me just stick that down a little better. Like determine the overall reaction, and then are there any intermediates, are there any catalysts, identify those as well. So what I like to do is just pretty much imagine like a line down the middle here, add up everything on one side, add up everything on the other side. So what I'll do is start just going literally like left to right chronologically. H2O2 plus I minus plus IO minus plus H2O2 yields. So it's like all the reactants yielding all the products essentially. H2O plus IO minus plus H2O plus O2 plus I minus. So now we have that. What we're going to do as our next step is we're going to cancel out anything that we have duplicates of, or it's on the product side and the reactant side. So first off, we have the I minus is here, I minus is there. So we're going to cross that out. Next thing we have is IO minus on both sides. IO minus here, IO minus there. Now we're left with, we have H2O here, O2. We have H2O2, H2O2. And those can't be canceled, so here's what it's going to be. 2H2O2. yields O2 plus 2 H2O. So let's look at what we have for intermediates, or everything that we canceled out. So for IO, we know we can look back to here. It started as a product and then it became a reactant. So we know, based on this here, it started as a reactant. It started as a product, then it became a reactant. So that fits the definition of an intermediate. So our intermediate is going to be IO minus. Now let's see if we have any catalyst. The other thing that we canceled out was the I minus. Now the I minus started as a reactant and then it became a product. And it also fits the other kind of the rough definition. It started in the first step as a reactant and then ended in the final step as a product. So based on this, that's going to be a catalyst. I minus. So now we've done that, and that's pretty good. We can move on from there and try to calculate what we're going to have here is the rate law. What we're going to have for that is K H2O2 I minus. Because what we're doing, we're taking this, the H2O2, from what we found to be our overall reaction, and it's similar. You might say it's still biomolecular because it would fit this one here. The 2A yields products. We have the 2 H2O2, and then we have the I. So what we're going to do, the I minus is here. Even though it was canceled out, it's a catalyst, so we're going to use it there because the catalyst helps the reaction occur. So there is our first problem. I think from there we're going to move on to our next one here. And I think I'll just cover this up for now to save some room. No, you know what, I'll move it down here. Okay, so in this one, we have a nitrile chloride, or NO2Cl, decomposes to nitrogen dioxide, NO2, and chlorine gas, Cl2, according to this mechanism. Now we have 3 steps, and we again have the fast, fast, slow. So a lot of times, like I said, the first question might be elementary steps. So our elementary steps we're going to break down. So we have, looks like we have our structure that's 2A yields products here. We have 1 mole of this product, 1 mole of this product, and then same thing in the last one. So it looks like all 3 are going to be bimolecular. And I think bimolecular is probably the most common. You won't find as many of the others. Termolecular is less likely as well. So here we have our elementary steps. So now we're going to find our overall reaction, and then we're going to say intermediates, catalysts. So let's see what we got. Again, we're just going to add everything on one side, add everything on the other. So we got, hopefully I can fit it all over here. 2 NO2Cl plus N2O plus ClO2 plus NOCl plus ClO. And then what I like to do sometimes if I run out of space or something, I'll actually write the product side on the bottom, and then you can compare them top to bottom, and that sometimes that view can help. ClO2 plus N2O. As you can see, these are going to be right above. ClO, NO2, NOCl, NO2, and finally Cl2. So now let's go back in and see what we can cancel out. So first off, we have our NO2, it's top and bottom, that's easy enough. The ClO2 and the ClO2. Then we have the NOCl, NOCl. This is going to be the case with a lot of these. Whenever you have a large reaction, oftentimes it's going to break down quite significantly. Looks like so. So the 2NO2Cl don't have that. We have the ClO. So finally, we're left with just these. So here we have our 2NO2Cl yielding the only things that aren't canceled out, 2NO2 plus Cl2. Great. So from there, what are our intermediates? So what are we looking for intermediates? They're going to be produced and then consumed. So right side and then left side. So from here we can look back. We'll just look at each thing that we canceled out. So the N2O, it started as on the the product side, and then it ended up in the reactant side. So one of them is going to be the N2O. Then we have our ClO. Where's that? ClO started here, ended here, same thing. ClO. And what else do we have here? Then we have our NOCl, same deal. And finally, we have our ClO. Oh, oops, I already wrote that. So yeah, we're just going to have those three intermediates here. And then let's see if we have any catalysts. We have 2, 3, 4 things canceled out. 2, 3, 4 things canceled out. And we have, my bad, so there is actually a ClO2, that's right. So that's another intermediate, and that means we're going to have no catalysts. Not only because none fit that definition, but also because we've just entered everything that we canceled out as an intermediate, so we can be pretty confident there. So the next thing that we can do here, I'll start writing over here now, I think. We have, what is the rate law? So first we're going to take the slow step. You always start with the slow step because the slow step is always the rate determining step, and that's, that makes the most sense that it would be involved in the rate law because, you have, what is it? You have your, it has the most impact on the reaction rate. Just like in a relay race, if you have like 2 really fast runners and 1 really slow runner, the slow runner is going to have the greatest impact on how fast the racers go, what their time is rather. So here we have the K3, NOCl, ClO. The problem is, and you can write these as like K1, K2, K3 for the corresponding steps. The problem here is this can't be the rate law because they're both intermediates. And you can never have intermediates. You can never have intermediates in your final rate law. So that's kind of a problem. What we're going to have to do is, they can't be in the overall rate law expression. I'm sorry. So I should have said expression here. So what we're going to use is we're going to use an elementary reaction for reaction 1. We'll start with the ClO. ClO is going to equal K1 NO2Cl. So we're simplifying it into, or we're doing the opposite of simplifying really. We're expanding it out into what it could be referred to as K minus 1. So K1 is going to be this way, K minus 1 is going to be the opposite. So for our K minus 1, what we're going to have is ClO2 and N2O. So that's our ClO. Then use the elementary reaction 2 for our NOCl, the other one. This one's going to be K2 N2O ClO2 over K minus 2, so the opposite, NO2. So now we've basically expanded those out into and expressed them as concentrations that aren't necessarily just the intermediates. So now we're going to substitute. So our K3 is going to be, it's going to get pretty long here. K2 is N2O, ClO2, all over K minus 2, NO2. Now it's this whole thing. Oops, sorry, I didn't even realize it was off. There we go. It's going to be this whole thing. We're just taking that from there. And then subbing in here, we have K1 of N2O. And we have our ClO. We have our K minus 1, ClO2, and our N2O. All right, so it's getting a little bit messy here, but essentially what we're doing is we're just putting these two things together. Instead of the NOCl, ClO, we're expressing them as their, kind of expanded out elementary rates. And now, basically what we're going to do from here is just simplify. So what do we have the same? We have a few things the same. We have the NO2 here. We have N2O here. We have N2O here. We have the ClO2, N2O and O2, and we can break it down to the following. K3, K2, K1, NOCl, NO2Cl, 2, all over K minus 2, K minus 1, NO2. So sorry about that again. So we have, basically we've just taken this and simplified it down to this. And why this final rate is going to make sense is because it has the NO2Cl, which we had over here, and then the NO2 here. And the reason why we don't need the Cl2 in the final reaction is basically because the Cl2 is just a product, and it's not going to be something that will determine the rate law, or the rate law expression rather. So that's going to be kind of our final answer for that. So these are, I think, pretty confusing, and it's going to get even more confusing on this last problem here. I'm going to see if I have actual room for it on this page or not. All right, so I just added a sheet of paper here on the bottom so I could accommodate this one here. This is going to be the next problem here. The overall reaction CH3COCH3 plus Br is going to yield CH3COCH2Br plus H plus Br minus. And it can be broken down into the following mechanism. So it might not even give you this reaction here. It might just say, hey, these are the steps, figure out what the reaction is. The reason I wanted to write it here is because we have the added difficulty of we're seeing the physical structures of some of these, and we have to break that down. And just one more thing that will add time, how long the problem's going to take, and just kind of make it like less convenient for you to do. So first of all, we'll say which step is the rate determining step. That one should be pretty straightforward. We're just going to look here at the slow step. It's going to be number 2. The slow step. And then the next question we say, what are the elementary steps? So what do we have here? We have 1 mole of this, 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 1 mole of this. Everything's going to be bimolecular again. again, just watch out for the 2A yields, yields products, or the 2A plus B. If it's 2, then you just really add up how many reactants there are, or how many moles of reactants there are. So then you have, it'll ask for the overall reaction. And in this case, they might ask for it, they might not ask for it. I've seen it asked like, hey, here is an overall reaction. Is this correct or is this incorrect? And then you have to find it and then compare it to that. That's one way that they could possibly do it. So in this case, we'll see what we get when we add this all up. And what I really want to do for this one, just because these are, you don't want to have to draw that many pictures to do the total thing. I'll start it over here. It's much, I think, simpler if you just write it out as the formulas. So that's quite a lot of reactants there. Now we have all right, so there we go. That's how long it would take to write that out. I think then this is probably a good time for anyone that wants to try the problem. Pause it here, see what you find for your overall your overall reaction expression, and then what are the intermediates, what are the catalysts. I'll write that in over here. All right, cool. So then I'm just going to start going through. We have our H3O. H3O, then we have the COH, then we have our H2O here, or H2O here. What else do we have? The CH, COH. Br2 we can't get rid of. CH3CO is not here, so we can't do anything about that. So we're left with 2 products and 2 reactants. So what I got here was, it's going to be CH3, CO plus Br2. It's going to yield CH2BrCO plus HBr. And here you can technically say, if you wanted to, you could say plus H plus, based on the fact that we can theorize that, like up here, for instance, it says that there's an H plus, it gives that to us. We can assume that that is there, but it probably doesn't play a big role in the rate or any of these reactions. It might be like, for instance, a 0 order, because, it is there, but perhaps this, just happened in a solution or something like that. And, the H plus is kind of an accessory, so to speak. But it would never be wrong for you not to include that, or at least that's my opinion. I think that that's why I put it in parentheses. I would honestly leave it out probably about half the time and leave it in half the time. It's just one of those things that maybe they want to know if you got it. Maybe you get a bonus point or something. I have no idea. But it's just, always worth checking this compared to what they gave you. And let's see. We have the CH3, CH3CO. The Br2, we have CH2BrCO, CH3COCH. All right, so here we go. We have CH3COCH2Br, and that is not what we ended up with. So this is a good point to check yourself. And looks like I forgot one of the CH3s. So CH3, CH2BrCO, CH3, CH2BrCO. That's what they had. That's what we had. And that looks like it checks out. Okay, so now we can keep moving forward with these. We'll see, are there any intermediates? we're going to assume that there's probably tons because we canceled out a lot of things. Now, we'll work through it piece by piece, but as far as the intermediates go, here again is the reminder. Our intermediates are going to be produced and then consumed in that order. So we'll just kind of go through these. CH3, CH3, COH. That one starts the OH here, and then it ends over here. So that's one of them. CH3, CO, or COH. Then our H2O starts here and ends here. So we got that. Then our CH3, CH2, COH is another one we have. The OH and then the OH. So that takes care of most of these. And then we have, let's look for catalysts. Remember our rule for catalysts? They're consumed and then produced. So a good place to start is see if there's anything that you have in the very first reaction as a reactant and then in the final reaction as a product. And we can look really quick. We see that isn't the case here, but that doesn't necessarily mean that we're not going to have a catalyst. So is there anything that is consumed and then produced? Let's see. Well, right off the bat we have the H3O plus, and that is consumed here, and then we get it out here. So it fits the category. It's consumed and then produced, or it goes from the left side to the right side. So it looks like one of our catalysts is going to be H3O plus actually. And then let's see, is there anything else? Nope, looks like we covered everything that we canceled out in this equation. So that is going to be our answer for that. So now from there, the next thing that we're going to do is, let me see, I think there's still a good amount of room here. We'll look at what we can find for the rate law expression. And like I said in the previous problem here, we're going to start by looking at the slow step and then work from there. What do we have for our slow step? Our slow step is going to be right up here. It's the CH3, CH3, COH, I believe. And then we have plus H2O. It's going to yield our CH3, CH2, COH plus H3O. And what that's going to be, it's bimolecular, which means that it's going to follow the formula of rate equals K2, we'll say, because it's the second experiment here. K2, CH3, CH3, COH, and H2O. So that is going to be the elementary step here, the elementary rate. And what's the problem here? The problem is these are intermediate. So we have CH3, CH3, COH right there, and then our H2O also an intermediate. So just like in the last problem, and this, if that's not the case, then you can really just use that. Again, we have two intermediates. We're going to have to get rid of them and figure out how we can, basically represent them in another way that doesn't include them, basically. So here's what you can start with. We're going to sub in from slow step. First of all, we can do this. We're going to take, so K2 of that, and then we have H2O and K1, which is going to be CH3, CH3, CO, and H3O. So all that, scoot that down, all of that over K minus 1 is going to be CH3, CH3, COH, H2O. So that's what this will result in once you substitute in for each of the intermediates that we ended up with the slow step from here. So the CH3, CH3, COH, and then the H2O. So now what we can do is just break this down. What do we have? We have H2O on the top, H2O on the bottom. We have the CH3, CH3, COH, top, bottom. So what we're left with is this, the CH3, CH3CO, and then the H3O. So what we can say is our rate is going to equal K, CH3, CH3, CO. H3O plus. And then from there, we can say rate is equal to K2, K1 over K minus 1, which is what we used here. So we're just taking the K's. And there is going to be our final answer for that. So yeah, these are really tough problems, I think, compared to a lot of the things in these chapters. But I just want to run back to the very beginning here. We had this important reminder here. Intermediates are produced, then consumed, so right, then left. And then the catalysts are the opposite. They're consumed and then produced, left, and then right. So yeah, hopefully this helps someone.